Good morning, everyone. My name is Janeshwaran Alaki Sugumadan. My matrix number is 229259, and today I am pleased to present my individual assignment focusing on transformative use case of modern technology implementing blockchain in supply chain management. Let's start with a fundamental question. What is supply chain traceability? Simply put, it is the ability to track a product throughout its entire life cycle from the very moment raw materials are sourced through manufacturing and distribution right down to the final delivery to the end customer. Why is this so relevant today? First, modern supply chains involve dozens of independent parties who don't necessarily know or trust one another. Second, counterfeit products are a massive global crisis causing billions of dollars in losses annually. On top of that, modern consumers demand absolute transparency about product origin and quality, while governments worldwide are tightening regulations on food and product safety monitoring. We need a system that can handle these pressures. Why blockchain? Traditional databases are controlled by a single organization. This means records can potentially be altered, whether accidentally or maliciously. Blockchain, however, introduces a paradigm shift by providing four core capabilities: immutable records, shared visibility among all stakeholders, product authenticity verification, and true end-to-end traceability. In this slide, you can see the essential fields required for our blockchain data structure alongside a conceptual diagram of a block. Let's break down how a block is structured and why these specific fields are absolutely necessary. Block ID serves as a unique identifier for each block in the chain. Product ID uniquely identifies each item, while batch number groups product from same production line. This is vital because if a defect is found, it enables precise, rapid product recalls rather than pulling everything off the shelves. The manufacturer ID definitely proves the origin of the goods, while the location field records the current supply chain checkpoint, giving us real-time tracking capability. The timestamp creates an immutable audit trail of when events happen, and the inspection results ensure that quality and safety compliance are met every stage. Digital signature prevents unauthorized updates, ensuring that only certified participants can log data. The current hash protects the block's contents from tampering, while the previous hash links it directly to the block before it. As you can see in the diagram, the block header contains the metadata, like the block ID, timestamps, hashes, and Merkle root. Beneath it, the transaction data securely stores the actual supply chain event, such as product P12345 manufactured by M001, currently in transit at warehouse KL with a past inspection status. To understand why we need this architecture, let's explicitly contrast a traditional database with a blockchain. Traditional systems in supply chains inherently suffer from information silos, limited visibility, a single point of failure, and high vulnerability to counterfeit risk. If we look at the architectural features, in control, traditional databases are centralized while blockchain is distributed across multiple nodes. As for data integrity, a database administrator can modify or delete records. On a blockchain, records are completely immutable. In the case of transparency, traditional systems offer limited visibility to external partners, whereas blockchain provides a shared ledger where all authorized stakeholders see the exact same data. In tamper resistance, databases are vulnerable to insider modification. Blockchain is heavily protected by cryptographic hashing. Regarding trust model, databases require you to trust a central authority. Blockchain establish trust programmatically through network consensus. Ultimately, blockchain is superior for supply chains because it breaks down silos, provides an immutable product history, makes authenticity verification effortless, and drastically increases consumer trust. Let us look at real-world threat scenario, product data tampering. Without a blockchain, a malicious employee or attacker could modify product origin information, change inspection results, replace genuine products with counterfeit products, or delete evidence of logistic errors. The consequences are extreme: consumer safety risk, financial losses, regulatory penalties, then finally damage to brand reputations. So how does blockchain protect us against this? It relies on four pillars. Firstly, we have cryptographic hashing. Every single block contains the mathematical hash of the previous block. If an attacker changes even one letter of the data in an old record, the hash changes immediately and completely. This instantly invalidates the block, breaks the chain integrity, and alerts the entire network to the tampering attempt. Secondly, we have digital signatures. Only authorized participants can submit records, and every update can be traced back to its creator. Thirdly, we have decentralization. Multiple participants maintain copies. Altering one copy does not affect the others. Finally, we have immutability. Historical records cannot be secretly modified. It is set in. Now, when implementing a blockchain, choosing the right consensus mechanism is critical. Many people immediately think of proof of work, the algorithm used by Bitcoin. However, proof of work is entirely unsuitable for enterprise supply chains. It is designed for open, anonymous cryptocurrency networks. It suffers from extremely high energy consumption, slow transaction processing speeds, and requires highly expensive hardware. In a supply chain where we already know who the business participants are, proof of work is an unnecessary waste of resources. Instead, I propose using the proof of authority consensus algorithm. How does proof of authority work? In a supply chain, we aren't dealing with anonymous users. We are dealing with known, legally bound, trusted organizations like certified manufacturers, logistic giants, and government inspectors. In proof of authority, these pre-approved, authorized organizations act as the validators who confirm transactions and build blocks. The advantages of proof of authority for this use case are immense. Firstly, it features incredibly low operational costs. Secondly, it allows for fast transaction validation, which is crucial for fast-moving logistics. Other than that, it relies on known participants aligning perfectly with corporate compliance. Finally, it uses very low energy, making it a sustainable solution for modern enterprise applications. That is all. Thank you.